Assalamu alaikum. Welcome back to a live session with Dr. Paul again. I'm delighted to see you again, Paul. I miss these sessions. We do them quite, haphazardly in terms of there is no, every 2 weeks or once a month. But it's really nice to always see you coming back on the stream.
I greatly enjoy it, despite the fact that it's a random distribution of dates.
Yeah, definitely. You've got some nice post-it notes behind you, and some is that just the different papers you are
Yes,
sort of
I'm writing a book actually on the topic of this lecture series, and I decided it was taking me too long to find my papers, so I'm starting to organize them.
Brilliant.
Yeah.
That's always the hardest part, organizing paperwork.
Yeah.
You should have a look at my desk right now. Okay, so as you guys know, we are continuing this series about testing universal common descent. This is part 4 of that series, but it's part 2 of Sober's paradox. So over to you, Paul.
Great. So I just will start with a quick outline of where we are going today. And I apologize to everyone, by the way, that I was not able to present this on the 18th as advertised. But I hope that even though it's coming at a somewhat later date, that it will still be interesting. So our motivating question is the following. Is there an overlooked problem in the logical structure of phylogenetic inference? So last time we looked at these 3 headings. Where are we located on the theoretical landscape? A common inferential puzzle in comparative biology, and that is observed similarity and what it means. And lastly, the consequences of improbable pathways. So today, we will define and examine Sober's paradox as Sober himself presents it, mainly in his 2008 book from Cambridge entitled Evidence in Evolution. But actually, it's a theme right throughout the past 3 decades of his work. And we'll talk about some aspects of the paradox that I think he missed or overlooked. And then we will begin to address where the paradox really comes home to roost, so to speak, in comparative biology by looking or beginning to look at the evolution of the ribosome, the molecular factory that is diagnostic of the living state on planet Earth. Viruses, I guess you could say by definition, lack ribosomes. They have to hijack them from a cell. And I think a strong case can be made on evolutionary grounds that the origin of the ribosome was the key event in the origin of life. Now, the problem with Roman numeral 5 is there's so much material to present that today I will just begin to address the question. And part 5 of this ongoing series will go into really the fascinating details of ribosomal structure and function. These sessions, I think you could probably look at viewership. As these sessions get longer and longer, viewership drops off, and I don't want to tax the patience of the audience. So I'm going to try to keep my remarks today in the neighborhood of less than an hour, I hope 45 to 50 minutes, so that, again, in the next session, whenever we're able to schedule that, we will go into the molecular details, which are fascinating. So spend most of our time here on Roman numeral 4, and then we'll begin to talk about 5. So in this part, we're going to examine the exquisite sensitivity of evolutionary and phylogenetic hypotheses to process assumptions. In particular, the widespread endorsement of historical singularities caused by improbable pathways. Zubor, do you know if there's any way if I can get that I can move this little box off of my
I think it says hide on the right.
But when I did that before, this happened.
All right. I guess that's fine then. We'll just have to make do with this.
All right. So now how do I get back to what I
You click back on the presentation.
let's
If you
see.
click on the beige area, just oh yeah, where that color is. What's that color again? Turquoise type of color. If you just click on that slide.
Oh, okay. All right. I'm sorry. This is a
There we go.
defect in the StreamYard software. I'll complain to the manufacturer. So the key points from part one, just to recapitulate for those who may have missed it or don't remember. What do I mean by theoretical landscape? Well, it's a landscape with 4 quadrants. And actually, I can show you them here. So we have no design, that is, the investigator makes no appeal or may even allow no appeal to a designing intelligence, versus design, where that is a causal possibility. And then, so this is you could call it the metaphysics of explanation axis of this landscape. And then here we have the geometry of life axis. Luca, the last universal common ancestor, existed such that there is a tree of life, or Luca did not exist and there's no tree of life. We are going to stay in the upper 2 quadrants here. Now, the reason for that is to keep the discussion manageable. When design is raised as a causal possibility, as it exists within, for instance, the intelligent design research community, the number of possibilities that one must consider for any historical puzzle just explodes. To my mind, this actually makes the science of intelligent design, even in its nascent state as we find it in November 2021, it makes it incredibly interesting, but it also makes problems like the ones we're going to be discussing much more complicated. So we'll stay up here as kind of, I guess you could say, almost an artificial restriction on the problem, but it keeps it manageable. Even though, of course, I think really to understand what we're looking at, we need to come down here. And maybe in parts 5 and subsequent sessions in this series, we can talk about the logical switchover point at which design becomes really compelling and forces the investigator to open up the other 2 quadrants. Anyway, that's something for a further discussion. All right. Also from part 1, evolutionary inferences to common ancestors and ultimately to the last universal common ancestor rest on the assumption of small probability causal pathways and event singularities. These pathways and events have the logical form: the origin of character X, whatever it happens to be, occurred only once, such that all X observed today trace their lineages materially to these historical singularities. This is a very common mode of reasoning. The origin of the first cell, or the origin of RNA, if you think about the RNA world hypothesis going even before the first cell, the origin of the genetic code, the origin of the ribosome. Characteristic of these singularities is the definite article the, right? The origin of the ribosome. So the markers in natural language are the definite article in 2 positions in those sentences: the origin and then the character in question, X, whatever it happens to be. It's a very common mode of reasoning. I think anyone who opens an evolutionary biology textbook will see it all over the place, okay? Now, as the probabilities of evolutionary pathways approach 1, unity, these inferred singularities dissolve away. And the reason for that is their evidential grounding is lost. What can or will happen more than once, given the right antecedent conditions, can then be posited as a spatiotemporal singularity only by stipulation. So that's a lot of verbiage, and I apologize for that. Let me give you an example. Let's imagine that the origin of the very large RNA molecule at the center of all ribosomes. We'll talk about this more in part 5. It's a beautiful, big RNA, huge, complex structure. Let's imagine that 100 years from now, some Nobel laureate has figured out the recipe for that RNA. In other words, in a one-pot reaction, providing the constituents, the chemical constituents of that RNA, he's able to show that there is a deterministic pathway to that ribosome or to that ribosomal RNA. Okay. And in fact, he says, this is the kind of planet where if you give me the right antecedent conditions, that RNA will fall out with a very high probability. All right. In a situation like that, which right now is science fiction, there is no known pathway to that very large molecule, which forms the peptidyl transferase center of the ribosome. It's the business end of the ribosome. It's where the peptide bonds are actually formed. And it's a major piece of evidence in support of the RNA world hypothesis. We don't know that pathway right now, but I can imagine a world in which we did. In such a world, the existence of that very large RNA molecule, which right now is taken as a marker of history of one of these singularities, that would dissolve away because you'd have deterministic pathways leading to that molecule with a high probability, let's say 1, just for the sake of argument. And there would be, the epistemological indicator of history would be lost. All right, I'll have more to say about this later on in the talk, but I spent some time on this in part 1 because it's very important. Hang on one sec. Okay, let's look at this one. These modes of reasoning, as I've indicated, are widespread in the biological literature. So let me give you an example. Here's William Martin, an outspoken, very feisty researcher in Dusseldorf, although he is an American citizen, but he works in Germany. I love reading his papers because he's very funny and he writes well and he thinks hard about interesting problems. In this paper in 2017, he was talking about the origin of mitochondria, and in particular, but also in general, the origin of the eukaryotic cell. And as you know, or probably know, the major hypothesis for the origin of mitochondria, that energy-producing cell organelle in eukaryotes, was via some endosymbiotic event where a cell, an archaean perhaps, incorporated an alpha proteobacterium, which was not digested, but set up shop, as worked out a deal with its host and said, I'll provide you energy if you don't eat me, and so forth. Martin says in this paper that event happened once in 4 billion years. And he says roughly at the same rate at which life and the solar system arose. So we're looking at a frequency here, pretty small, right? You need a very large window of time, 4 billion years, and you're going to get this event once within that span of time. Okay. Now, you might ask, well, how does he know this, right? How is that frequency determined? Is it known experimentally? Is it known observationally? Or is it an unsupported postulate and thus possibly false? All right. Notice as a general logical point, the structure of reasoning here. He's invoking a singularity. That happened once. Okay. These singularities will be critical to the logical structure of what I'm calling Sober's paradox. So Sober, throughout really the last 3 decades of his career, arguably even longer than that, has been occupied with these questions. So the University of Wisconsin-Madison is just a couple hours north of me. And when I was a graduate student and then at professional meetings and so forth, I would interact with Sober. And it's clear that these questions are sort of his daily bread, so to speak. He really gives them a great deal of thought. So he has consistently argued in support of a comparative likelihood framework for understanding how we can reliably infer unobserved and indeed unobservable past events to explain current evidence, using what Hacking in 1965 dubbed the law of likelihood. Now, please don't be put off by this formula. I'll kind of walk you through it here. We've got H1 and H2, and these are empirically incompatible hypotheses, meaning they assert things about the world that cannot both be true, or they cannot be true at the same time, such as there was a last universal common ancestor to all Earth life. There was not a last universal common ancestor to all Earth life. So these are hypotheses that make au fond incompatible claims, empirically incompatible claims about the observable world. So in a case like this, likelihood is going to give us, or this likelihood framework is going to give us what's known as a likelihood ratio. And these symbols here stand for hypotheses, H1, H2. E stands for evidence. P is the probability. So the law of likelihood tells you the probability of hypothesis 1, given this vertical line here is a conditional symbol for conditional probability, given the evidence, H1 will be better supported than H2. So if we take an equivalence here, let's say these probabilities are equivalent at this point, H1 is going to win or be stronger in the likelihood ratio if and only if the probability of the evidence given H1 is greater than the probability of the evidence given H2. All right. So as I said, don't let the formula throw you. An example will help. Let's suppose H1 is someone's infected by a SARS-CoV-2 carrier. My wife and I just did a test. We're tested for SARS-CoV-2 because actually tomorrow morning we're going to fly east here in the United States to spend time with our family for the Thanksgiving holiday. And I'm happy to report neither of us has, at least at the sensitivity of the particular test, any evidence of we've got SARS-CoV-2. So H1 is somebody was infected by a SARS-CoV-2 carrier, and that's why they have the virus, versus H2, which was that person evolved something in their biology allowed them to evolve a single-stranded RNA virus closely resembling SARS-CoV-2, and this happened entirely independently of the virus that we're all worried about. If you'll excuse me for just a moment, I have to let the cats out of my office.
Sure. No problem at all. A life with cats is a happy life, I have to say.
Except when they insist on requiring attention during a podcast. All right, they're out.
Yeah.
Or I should say an online seminar. Okay. Now here, our probabilistic intuitions tell us reliably reduce appeals to luck or coincidence. So H2 would require an enormous helping of luck a huge and improbable coincidence such that by some unknown pathway, an RNA virus evolved de novo in this one individual that just happens to be indistinguishable from the virus that we know about. So here, clearly, the likelihood ratio is going to favor H1 because all the background knowledge we bring to the question tells us that's much more plausible. All right, so it's not really that complicated. It's just formalizing the intuitions that we all carry around about how we make these judgments of the relative strength of hypotheses conditional on the evidence. Okay, reduce appeals to luck. Keep that in mind because that will be relevant later on in the presentation. Okay, here's how Sober puts the point in his 1988 book, which I actually have here. This was his first major treatment of these kinds of inferences, reconstructing the past, which you can see I wore out over the past 3 decades, published by MIT. Here's how he puts it. A correlation, in our case, the observed similarity between 2 events might be explained by postulating 2 separate and independent causes, but this explanation would make the correlation too improbable. Okay, and those are his italics. A common cause explanation is preferable because it makes the observations less of a miracle. It is more plausible because it strains our credulity less. The operative idea here is likelihood. So consistently throughout his work on these questions, Sober has favored this comparative likelihood framework, and I think it does have much to commend it. Again, this fits with our probabilistic intuitions, but, big red but, okay? Difficulties arise when we interrogate these intuitions against different possible backgrounds. And to see this, we need to do a careful thought experiment. So let's do that. Time for a thought experiment. So here's Alice, who is a molecular biologist. She's a geneticist. And Alice isolates and sequences a gene that looks like this, DNA sequence. Okay, 5' to 3'. Here is the nucleotide. Base pair by base pair sequence. Let's call this gene A for Alice. This is Alice's gene. All right, simultaneously, but working without any knowledge of Alice or her new gene, Bob, here he is, he's another geneticist, isolates another DNA sequence from a different species. So there is Bob's gene, 5' to 3', base pair by base pair sequence. We'll call that gene B for Bob. And then, having done this, Alice and Bob each separately form origins hypotheses about how A and B arose historically. All right, so these will be evolutionary hypotheses about the first origin of A and the first origin of B. But it's important for this thought experiment to make sense that Alice and Bob have no knowledge of each other. In particular, they have no knowledge of each other's, at this point anyway, of each other's gene sequences or hypotheses. So they're working entirely independently at this point. Okay, there's Alice's gene, there's Bob's gene. So Alice hypothesizes that A arose by an improbable causal pathway that occurred once in 4 billion years. All right, so let's call that H1 from starting point X. Now, this cartoon, the reason for the triangle for that shape is I want you to think of A just exquisitely balancing on the point of that triangle. All right, so this is just a schematic way of representing an improbable pathway. A lot of things have to go right for A to have arisen, and A is just balanced there on its pathway, exquisitely balanced. All right. Now, notice what I've done here. I've just borrowed that that probability or that frequency that Martin proposed for endosymbiosis. He says, look, it's rare, once in 4 billion years. So I just borrowed that from him for the sake of the thought experiment. All right, here's Bob with his gene. And again, remember, Alice and Bob are working independently of each other. They don't know about each other's hypotheses or the genes. He starts from H2. He also uses that once in 4 billion year frequency. X and Y, these two starting points are spatiotemporally distinct. In other words, on the Earth, these are separate causal theaters. In the hypotheses that Alice and Bob formulate, you could say that, let's say H1 is somewhere in the Pacific Ocean at a submarine vent, and for Bob, it's somewhere on Greenland in an ice chasm. All right, so these are spatiotemporally distinct theaters where these hypotheses are getting up and running. Now, later on, Alice and Bob learn about each other's genes and causal hypotheses. It turns out that these genes code for catalytic RNAs, which seem to be functionally related. When the role of the sequence is examined in cell biology, it appears to be very similar. Okay? Catalytic RNAs are functional products that are not translated into protein. The single-stranded RNA has the remarkable feature that it can fold, and base pairs, you get complicated hairpins and bubbles and all kinds of interesting structures in RNA. DNA is very boring, frankly, by comparison. It's a wonderful repository, library of information. But RNA, I would say far more than DNA, is really the secret to life on this planet. When you look at all the different roles that RNA has within cells, I don't mean to belabor the point, but these are functional RNAs. They are not going to be translated into protein. So Alice and Bob, now that they're in communication, they say, well, you know what? Let's see if we can align our genes. So they submit them to a standard DNA sequence alignment algorithm. And there's the alignment. Okay, we just put the 5' end at the same position. And the algorithm, as these software packages do, it finds multiple regions of identity between the two sequences, indicated here by the red hatched lines, where base pair by base pair, the sequences are identical. So actually in this top alignment, we've had to introduce a gap here, but alignment software will do that to optimize the alignment. Small gaps can be introduced, and of course there's an associated gap penalty with doing that, but it's not a big gap. It's only 5 base pairs. So to optimize the alignment, we introduce a small gap here, and we get these nice regions of identity between the two sequences. Now, you show this to someone who does molecular phylogenetics, and they're going to say almost reflexively, these sequences are homologous. When you have that degree of similarity, and we won't beg the question at this point by calling it homology, when you have that degree of similarity between two sequences, that calls for explanation. And it turns out that these sequences of identity correspond to secondary structure motifs in self-cleaving RNAs. That's what they do in the cell. All right. Now we've got a puzzle, right? We need to sort out Alice, or adjudicate between Alice's origin scenario and Bob's origin scenario, because clearly these two sequences, A and B, have some kind of relationship to each other, right? Either they arose separately or they share a common ancestral template. So we call in a leading evolutionary biologist. Let's call him Dave. There he is. And we ask him to apply widely accepted evolutionary principles, which we'll see on the next slide. We want him to adjudicate between Alice and Bob, between Alice's hypothesis for origins, which again posits a spatio-temporally distinct theater from what Bob has. So we say, Dave, A and B appear to, by all accepted criteria, to be homologous. Which origins hypothesis is correct, Alice's or Bob's? So Dave applies a principle that lies at the foundation of molecular phylogenetics. And here, this is actually a direct quote, which I gave last time. Here it is again from Colin Patterson, a great systematist at the British Museum. He died in 1994, but he was very influential during his career. And writing on the question of molecular homology, he put it this way. But this would be accepted, I think, by almost any investigator in molecular phylogenetics. Convergence between molecular sequences is too improbable to occur, just as similarity between sequences is too improbable to be explained except by common ancestry. This is the argument from complexity. If two structures are complex enough and similar in detail, probability dictates that they must be homologous rather than convergent. So we say to Dave, apply Patterson's principle, which really is one of the foundation stones of molecular phylogenetic methods, really going back decades, and give us a definitive ruling. Okay, now, pay close attention to this slide. In one sense, it's probably the most important slide in the presentation. Dave says, all right, let's compare the two, or let's ask which of them can be true with respect to the other. Can they both be true at the same time? Well, he says it might be that Alice's hypothesis is true, but then Bob's has to be false, because given the degree of similarity between these two genes, they require a common ancestral template. So if we start with Alice's hypothesis and say that's the true one, then Bob's has to be false because it invokes a separate theater of origins. So Bob's sequence has got to stem from Alice's at some point. So Dave says, Alice's hypothesis can be true, but then Dave's has to be false. That outcome is possible, says Dave. Or reverse it. Let's say Alice's hypothesis is false, but Dave's is true. Okay, because given the degree of similarity between these two genes, they must share a common ancestral template. So if we say that Dave's got the right story, then Alice's is false. That outcome is also possible. Or they could both be wrong, right? Both of their hypotheses are false. There's some third hypothesis that is actually the correct one. They're both false. But this is what cannot happen. They can't both be true. This outcome is not possible. Okay, what you see on this slide is pervasive throughout the molecular phylogenetics literature. When evolutionary biologists think about how they are going to explain degrees of similarity between molecular sequences above a certain threshold, they do not allow this possibility. All right? It's just off the table. It's considered not possible in light of the principle that was laid out on the previous slide from Patterson. Okay, let's keep going now with our thought experiment. This outcome is not possible. Both of these hypotheses cannot be the case once the degree of similarity between A and B crosses a certain threshold, because these hypotheses invoke independent origins, spatiotemporally distinct. Now, Dave says, come on, Paul, this is just biological common sense. If two structures are complex enough and similar in detail, probability dictates that they must be homologous rather than convergent. A and B must share a common ancestral template. And then he expresses some impatience with the whole thought experiment. It's contrived. Making up DNA sequences, that show high similarity and pretending that they could possibly have independent origins is silly. Now, here's the twist in our thought experiment. The sequences that I showed you are not fictional. They evolved, or they were evolved, in independent lab populations in Boston, in the lab of Jack Szostak. And this paper in Nature describes what they discovered. Remarkable paper published in 2001. And what happened was they noticed that these motifs, these RNA sequences, had a very curious phylogenetic distribution. Look at the abstract here from their paper in Nature. They were found in the genome of a newt, in cave crickets, plant viruses, and schistosomes. Okay, so this is all over the tree of life, right? This is not a coherent clade. Plant viruses, schistosomes, newts, crickets, all right? Yet they all had these same, what are known as hammerhead ribozymes. So they did the experiment that naturally suggests itself. They said, we wonder if we can get this same sequence, if we can breed it in very large RNA populations. And that's what they did. And here is a selection. So the columns here show the alignment, and the rows are different samples from their RNA populations that they were able to breed. If you show this kind of alignment, again, to a molecular phylogenetics person, they're going to say those sequences share a common ancestor. That degree of similarity, where you get just columns that are base pair by base pair identical over the length of the sequence, they say these share common ancestry, even though they don't, right? These are independent offspring, if you will, of RNA, call it RNA breeding. Okay, so I highly recommend this paper. It's 20 years old now, but the implications of the paper have not faded with the passage of time. If anything, they've grown stronger. So in the paper, in Nature, they say, our results suggest that the evolutionary process may have been repeatedly channeled in nature as in the laboratory towards repeated selection of the simplest solution. This is the secondary structure of the hammerhead, which performs this self-cleaving function. So where did Dave go wrong? Of course, Dave is our stand-in for the molecular phylogenetics community. This is what we observe, all right? Similarity between sequences. Everything below in the gray box is inference. It is critical to keep this in mind, that similarity is the observation, homology, or homology here from a common ancestral sequence, or its absence here in the independent origin scenario, that is inference. So one of the members of my committee at Chicago, Lee Van Valen, put it beautifully in a letter to Nature in 1983. And I think, be a very strange bumper sticker, but it would be a good bumper sticker, or maybe poster on a wall in a molecular phylogenetics lab. Homology is always an inference, said Van Valen, never an observation. What we observe is similarity or identity, never homology. All right. It's a dictum that one should bear in mind. Observe similarity, even identity. We had identical strings in those two genes that I borrowed. I borrowed those sequences from the Szostak experiment on the hammerhead ribozyme. That phenomena, those data do not tell us by themselves which causal process is responsible to explain the phenomena. All right, so Professor Dave's intuition was that degree of similarity, if the origin of the initial template was via a small probability Markov chain, that's going to be an exceedingly small probability pathway. If you have that in the back of your mind and you see similarity between genes A and B, or genes A, B, and C, and so forth, you're going to be drawn gravitationally towards the hypothesis of common ancestry. But of course, that's not the only possibility. So I showed these little diagrams last time to help give you a representation of different modes of causation. Here we've got, this is a randomizing cylinder that would be suitable for a lottery, right? Or some drawing where we want chance to run the show, because we can't follow the process. Once we turn that crank, we are introducing a randomizing process that we cannot follow, and it effectively becomes a chance. The sequence of balls that we extract, we say justifiably was caused by a chance process. That's not so here with the funnel. You pour the sand in, you pour in the fluid, it's all going to come out at the same spot. So you're determining an outcome in this case that you would not be able to do here. So in their paper, Shostak and Salahi Ashtiani, I'm sorry I'm not doing a better job of pronouncing that person's name. They write very nicely in their conclusions. Our results show that despite the dominance of contingency, historical accident, so this is contingency right here, lottery cylinder. Despite the dominance of contingency in some recent discussions of evolutionary mechanisms, purely chemical constraints, that is, the ability of only certain sequences to carry out particular functions, can lead to the repeated evolution of the same macromolecular structures. So you can see how you've got different causal backgrounds will give you very different sets of intuitions with respect to explaining similarity once you're confronted by it. All right. Dave got it wrong because he assumed small origination probabilities when in fact they were effectively at unity in making this comparative judgment between these two scenarios. All right. We come to the point now, the thought experiment is over. We can now give Sober's own formulation of what I'm calling his paradox. And he expressed it in this book, 2008 monograph from Cambridge, which again, I recommend to you. Somewhere around here, down on the floor there, I've got my copy. Again, I've worn it out with use. Wonderful treatment of these questions. Here's how he puts it on page 304. Here is the general pattern. And these italics, by the way, are in the original. He really wants you to see this. The more improbable it is that an ancestor has trait T, the stronger the evidence that X and Y's, those are two species, two different species, having T provides for their common ancestry. Let me read that again. The more improbable it is that an inferred ancestor has trait T, the stronger the evidence that X and Y having T provides for their common ancestry. Now, improbable here refers to a causal chain. The value we give to the events in a causal chain leading to the first origin of trait T. That value rests entirely on what we know about the evolutionary processes at work, which we infer must have led to trait T. So where does improbable come from there? That adjective in Sober's expression of the paradox, it comes from our knowledge, or frankly, our lack of knowledge about the pathway leading to the first origin of T. Okay. So to use this schema, which I've shown now many times in these talks, if the pathway, remember the reason for this triangle is trait T is balancing very, very gingerly balancing on the point of that triangle. That's an improbable pathway. If that's the origin of T, then we can also model it on the lottery cylinder. We put it over here. Because these are independent events, the product rule will hold, and this independent origin scenario on the left is going to lose every time. So this is just a cartoon representation of what Sober mathematically lays out for you in the 2008 monograph. And again, this makes sense, right? Only if this origination probability is small. Because as you change it, all right, last time I talked about a red bead on a wire, I actually made a red bead on a wire for myself, just as a little toy. So you could say my left hand here is probability 0. My right hand is probability 1. That's the probability interval. And as I move my bead over towards 1, this framework that I've shown here on the slide ceases to work, ceases to apply. But I want to stay with Sober and his expression of the paradox. The non-paradoxical aspect of the paradox is avoid appeals to luck. And our practical reason depends on this, right? If we've got independent events with independent probabilities, when we're evaluating them as part of an overall scenario, they multiply. And the product of those probabilities for events 1 and 2 and the whole causal chain is what we need to evaluate. There's a scene in the movie Casino directed by Martin Scorsese that I was not able to find, and probably that's a good thing because there's a lot of profanity in the scene. But if you've seen the movie Casino, there's a scene about in the middle of the film where 3 big payoff slot machines, right? These pay out huge awards. 3 machines in a row have been hit at the same time. All 3 paid out on the same day at the same time. And Robert De Niro, who plays Sam Rosenthal, can't remember the name of the character. Anyway, he's the manager of the casino, running the casino. He's livid. He's really upset with the guy that runs the slot machines, the casino employee responsible for these 3 slot machines. And the employee says, well, it's a casino. Sometimes people have to win. And De Niro says to him, you don't understand. These are independent machines. They're supposed to be independent. You can't win all 3 of them at the same time because of the product rule. The probability for a single machine is sufficiently small that when you take all 3 in tandem or in sequence and multiply, that's just never going to happen unless there was some cheating, right? It's a great scene if you ever see it, and sometime I'll excerpt it and beep out the multiple F-bombs that occur during the scene because it illustrates this point. Okay, that's not paradoxical. Avoid appeals to luck. Paradox comes in when we go back into biology and analyze hypotheses of common ancestry. So here at the top of the slide, I have Sober's expression of this paradox, which again, in the original, he puts it in italics. He doesn't want you, the reader, to miss this. Okay, what does this entail? All right, print it out and sit and think about it. If this is true, it has all kinds of curious consequences. I'll mention just 2 of them today. We'll talk about more next time. This statement, if it's true, entails things like the following. The less we know about the experimentally demonstrable or repeatable details of the evolutionary pathway from ancestral state P to trait T, right? So there's some pathway that we want to delineate, we want to understand. The less we know about that pathway in terms of experimental demonstration or repeatability, where we understand each step and why one step leads to the next, the more compelling trait will trait T will be when we find it in species as evidence of their common ancestry. To put it more simply, the less we know about the origin of trait T, the more confident we can be that that trait evolved from an unknown common ancestor P. Now, that is paradoxical, because what this says to evolutionary biologists is if you have a similarity in multiple species that you infer must have had a common ancestor, the less you know about how that trait evolved in the common ancestor or might have evolved in the separate species independently, the less you know, the more confident you will be that there must be common ancestry, okay? You can see this clearly in the literature about the origin of the so-called universal genetic code. So in 1968, in a widely cited paper, thousands of times cited paper by Francis Crick, he proposed what was called the frozen accident theory for the origin of the so-called universal genetic code. Now, an accident in this sense is a chain of in principle irreproducible events. These are one-off occurrences that are probabilistically identical to a randomized draw from a lottery cylinder. So again, keep this model in mind. All right. The paper by Crick is widely cited. Not a lot of people actually read it all the way through, because when you get to the last paragraph, it's clear Crick does not like his own proposal. He does not like his own frozen accident theory. So here's how he puts it at the end of the paper. This is in the last paragraph. The theory seems plausible. This frozen accident theory seems plausible, but as a theory, it suffers from a major defect. It is too accommodating. In a loose sort of way, it can explain anything. A second disadvantage is that the early steps needed to get the system going seem to require rather a lot of chance effect. Okay. Crick, on the topic of the origin of life, and this is clear from his 1981 book, Life Itself. On the topic of the origin of life, Crick was always deeply uneasy. And work that he did, like this widely cited 68 paper, led him in later years to propose panspermia, which is the hypothesis that he presents both in the technical literature, but also develops in greater detail in the book Life Itself. Panspermia holds that an alien intelligence, for reasons that are hard to discern, but who knows, it's not really relevant to the hypothesis, sent life here in a spaceship. That name, panspermia, literally means that, right? It's a good name for the hypothesis. Rather, a lot of chance effect troubled him. It troubled him. And it brings us to the second entailment of Sober's paradox. All right. I'm going to skip that previous slide. There again, I have Sober's formulation of the paradox in the box at the top of the slide. Johann Wegle is a German systematic biologist who works on the logical structure of phylogenetic inference. He is worried, and it's clear in his 2005 book, about the requirement to keep these small origins probabilities and the pathways leading to the origin of new traits exquisitely poised right near zero, right? So here's my bead on a wire. For these inferences to common ancestry to work, the origin of traits has got to be effectively over here in the immediate neighborhood of zero. These are singularities. They happen once. As we saw at the beginning of my presentation today, William Martin at Dusseldorf says endosymbiosis once in 4 billion years, that was a one-off. Okay. So in his 2005 book on the foundations of phylogenetic inference, Wegle says he's troubled. He says the fact that the probability of a multiple evolution of identical complex structures is low does not mean that complex organisms should not evolve at all. What's the problem? The problem is that probabilities that live in the immediate neighborhood of zero, they're just barely right on the positive side of zero along the probability interval here. How do you know that they happened at all? Because what you're invoking is something that is effectively indistinguishable from a naturalistic miracle. And Wegeley, as he reconstructs phylogenetic inference, he says we have to have these things happen, but in order for us to invoke common ancestry, they can only happen once. And things that can only happen once are teetering right on the edge of not happening at all. Okay, so I'm going to talk more about this next time with respect to the ribosome. But this is a point at which, in that landscape I showed you at the beginning, you can look over the hill and see intelligent design just on the other side of the hill. Because when you come to the point in your reasoning that you are invoking naturalistic miracles, you may as well stop doing that and move into a different sphere of reasoning. So this is a point at which, by different sphere of reasoning, what I mean by that is change your metaphysics of explanation. And again, I'll say more about this next time with respect to the ribosome. So here we are, part 5, the evolution of the ribosome. Now, where the paradox comes home to live and actually bites you in the backside. Here's a slide from Professor Jonathan Eisen, who is a professor at University of California, Davis. He does work actually on the tree of life. He's does microbial genomics, has published a number of influential papers on the topic. This is from one of his lectures to undergraduates. All right, this is the actual slide. Now, the topic that he is discussing in this lecture is homology, that is similarity that gives you a reliable signal of history, right? Versus homoplasy, which is similarity that's misleading. Homoplasy is the enemy of phylogenetic inference. What you want to do is build a stable tree of life using similarities. You want homologies because homologies are giving you true history. Homoplasies are similarities that will mislead you. So in this lecture, Eisen is sifting between homology and homoplasy and is saying, he's asking, how do we know when we've got homology? Well, he looks at the ribosome, this enormous molecular factory, about 53 proteins in its simplest form and 3 very large RNAs. Talk more about that next time. What does he say? Well, look at the figure. What he says is there's no way this could have happened multiple times independently. All right, so this is his actual slide. No way, all caps. Uses ribosome for translation. You could call that a character, ubiquitous character in life, actually. Could have evolved in separate origins of life. The only possibility is a single tree, right? So the ribosome is going to be present in LUCA, and it will branch to the ribosomes that we see in the other domains, in archaea and eukarya. Now, when you see a slide like this, or a figure like this, the figure represents an argument. The figure represents a series of assumptions or premises that issue in this diagram. So what's in the background here for Eisen, and I would say for most molecular evolutionists, is this initial branch. Going from the prebiotic environment, prebiotic milieu, somehow the ribosome got up and running. Now, why doesn't he show this with multiple events happening, with multiple origins of the ribosome, which actually, as I'll discuss next time, was Carl Woese's view, remarkably, who really gave us the three domain picture, all right? The reason he doesn't do that is he's assuming that this pathway here to the first ribosome was a very small probability series of events. And if we go back to the schematic that I've showed you now many times, he's saying it's just not reasonable to postulate multiple pathways like that. You're just going to be lucky to have it once. No way. No way it could have happened in separate origins. Now, again, I said the diagram conceals an argument, or the diagram is based on an argument. Look at these branches. These are what I'm going to call, or have called, transition probabilities. So what Eisen is postulating here is the origin of the ribosome. All right, let's say sequence X is the very large RNA that forms the peptidyl-transferase center of all ribosomes. The origin of that was a very small probability Markov chain. We're just lucky to get it at all. But then it has to vary, because we're going to have different ribosomes depending on what groups we look at. So we've got these transition probabilities. When you make this kind of argument, you are saying this is possible. It is possible to go from an unknown common ancestral form to branch out, right, into this phylogeny to give you the different ribosomes that are present in different groups. Okay, next time, what we're going to do is look at or ask what evidence is available for these transition probabilities. And just to whet your appetite, and I've run way over now, so I'm going to stop at this point. There is remarkably little evidence that this can happen. In fact, it's really astonishing. And one of the tasks I've set myself before the next presentation is to make sure I have scoured every corner of the existing literature on ribosomal evolution. It's a big task, right? But I'm kind of a nut for the literature. You can see it here, right? Arrayed behind me. In fact, if I turned this computer over to that wall, there's a whole lot more of this over there. So I have set myself the task of running to the ground the available literature on ribosomal variation. But I can tell you my preliminary finding, almost nothing. In fact, I'm hoping to excerpt a YouTube video from Lauren Williams. Really great video, very entertaining. I recommend it. I'll send the link to Subor, and along with all the references as usual, where someone asked Williams in an online seminar, what's the evidence that the ribosome can vary by random mutation? And he says, I'll paraphrase, he says, that never happens. We have no in vivo evidence of that ever happening. All right, so spoiler, tiny spoiler for next time, there's very little evidence that this actually happens, at least in terms of the ribosomes that we know. And so ask yourself the question, what happens if these transition probabilities are set at 0? All right, because when we're doing this comparison, we're evaluating this entire scenario versus this entire scenario where numbers have to be put on all of these branches. Anyway, I apologize. I meant not to take this long, but we're well set up for our ribosomal adventure in part 5 next time. And we have a few minutes for a little Q&A with Subor. Should I stop my sharing?
Yeah, that's brilliant. I can just take that off. So thank you, Paul. That was a great presentation as always, and lucid as well. So in terms of when you were mentioning about, you know, two different scenarios which are spatio-temporally distinct, essentially everything still boils down to the origination probabilities which you previously covered. I wanted to bring in something I heard Jonathan Wells saying. This is some time back, but it's still quite relevant. It's what the philosopher Ronald Brady says about by making our explanation to the definition of the condition to be explained, we express not scientific hypothesis but belief. We are so convinced that our explanation is true that we no longer need to see that we no longer see any need to distinguish it from the situation we're trying to explain. Dogmatic endeavors of this kind must eventually leave the realm of science. This is exactly what I was thinking. This quote was just jumping at me, and that's why I had to quickly go find it when you were going over this presentation, because essentially none of this seems scientific at all.
Well, my criterion for scientific, to sort of flesh out that adjective, is testability. So if someone forms a hypothesis about the origin of RNA, the origin of the first cell, the origin of the ribosome, because I don't see any deep in principle distinction between what some people call operation science and origins science. All science is inference, right? Yeah. By its very nature, all science is inference. A bunch of high school kids doing a simple physics experiment where they have a inclined plane and they're, measuring the velocity of a ball on an inclined plane, or they've set up a pendulum. It's all inference. Some chains of inference are a lot longer than others. And that's the case for the so-called historical sciences, where you have long and very delicate chains of inference. But if you can show me a way that you can check your own hypothesis, you say, well, if my hypothesis were the case, I would expect to see the following. I'm willing to say, well, you know what, I'll call that science, and let's go look. Let's go see if what you predicted is the case or not. So the problem I have with many with many hypotheses in historical biology is the assumption of common ancestry is baked into the method.
Yep.
Right? I think that's what you're getting at with Brady, with the quote from Brady, who I wished was still with us. He had, again, was one of those people who died tragically young. But Brady was able to say, looking at many areas of evolutionary theory, you have baked in to your analysis the conclusion that you claim will come out at the end.
Yeah.
And one of the, actually more than one of the chapters in the book I'm writing on the theory of common descent looks at the methodological scandal of phylogenetic inference, even at the point of aligning sequences. So I showed a simple alignment in my thought experiment, but alignment methods historically have been plagued with circular reasoning.
Oh, yeah.
The problem is, for an investigator who takes common descent as part of the furniture of reality, they are unconscious of the fact that the conclusion has been baked in, to use that term. And I think that's changing. I'm enough of an optimist to see that indications that more and more investigators are conscious of the fact of what they're presupposing, and that may be affecting their inferences. It's being forced on them by genomic data in many cases.
Yep. And could we also say that, just to summarize their argument, essentially when they use these arguments about similarities in anatomy and DNA sequences, essentially they are making at least two presuppositions. So they are assuming the origination probability is 0 and the transitional probability is close to 1. So normally the way that I've seen people interact with these claims and to try and push back is by actually not challenging these presuppositions, or these presuppositions don't even boil up to the surface, is usually about, well, if we were to apply your maximum likelihood method, then we'd come across these inconsistencies, and then they would turn around and say, well, that's convergent evolution or homoplasia, whatever it is. And that's where the debate ends up, rather than the foundational issues which you're highlighting.
Yeah, I think that's right. And in my lifetime of thinking about these questions, I always want to climb up higher in the logic tree, um, because it's often at maybe I shouldn't say higher. If you think of a tree, if I'm going to use the metaphor of a tree, I want to go down to the root,
Yeah.
down to the very foundation of the method, and it can create some discomfort actually in conversation with evolutionary biologists who find it I wouldn't say disingenuous, but they find it troubling to reopen these foundational questions. They say, look, Paul, it's just the case that life on Earth shares a common ancestor. Get over it already,
Yeah.
right? It's like approaching an astronomer at a cocktail party and asking him, what's the evidence that the sun goes around the Earth? And, he's going to glance down at his watch and say, what, thinking to himself, what's the first socially appropriate moment that I can get away from this person, right? He's clearly a crank. And in my own lifetime, I've watched questions that I asked in the early 90s with evolutionary biologists, like, if the theory of universal common descent weren't the case, how would you know? That question has moved from the annoying philosophical periphery of the discipline right now into its center, where investigators like Eugene Koonin, who are definitely not intelligent design advocates, are now entertaining this question. And I'm happy to say, again, as I did a moment ago, it's the genetic data that are pushing it, right? They're forcing the reopening of these questions. But philosophers get away with asking annoying questions, although unfortunately that's how Socrates ended up, having to drink the hemlock. So
Yeah.
it's an occupational hazard.
It is. It is definitely. And another way of thinking about it is if we go back to say the 19th century, and there was to be a discussion between the astronomers and the physicists who wanted to retain the Newtonian worldview. There would be these sort of discussions about Vulcan and between Mercury and the Sun, and all these sort of intricate answers that they had, but the foundational assumption of time and space being fixed was unchallenged. And until Einstein came some decades later and showed that centuries later, and actually showed no, time and space can actually be flexible, then, until then, Vulcan was a serious thing and people had to have these discussions. So I feel it's the same thing that even with Einstein, it wasn't just so much of a pure data approach he had. He had to conceptually step out and become a philosopher for a bit, and then come up with these sort of solutions. So I guess the same sort of revolution eventually needs to take place in biology.
I think it's happening. I see indications at meetings and in the literature of people asking questions like, really, how do we know? How do we get to homology from the observation of similarity? As I said with that slide, citing Van Valen, similarity is what we observe, and then we bring assumptions to play that make homology, meaning inference from descent from a common ancestor, more or less plausible. And every science, as you walk around, it's think of it on the model of a town, right? You come to the border regions where it can get rather scary because philosophical questions and conceptual questions raise their heads, and they are unpredictable. If you're Einstein and you say the notion of simultaneity needs analysis, right? So you look at his beautiful 1905 paper on special relativity. There's a big section in there where he carefully dissects the notion of simultaneity in order to move beyond this Newtonian framework that he felt had broken down. So I encourage evolutionary biologists when I am in conversation with them to think about these questions, even though it may make them uncomfortable. Because it's at these deeper levels that you may find that there's an assumption buried that's misleading you.
Yep, absolutely. So, Paul, it's been a great session. Thank you so much for your time. I really do appreciate it. I think this is probably one of the best live streams I enjoy, because we're getting down to, I guess, I mean, the analogy you gave was like a town and going into the border regions. But I think for many Darwinists, we're dragging them into the twilight zone, a place where they don't really want to, be. So, Paul, it was great having you. We'll sort out another time to bring back.
Ribosome.
Yeah, that's it.
The beauty and the mystery of the ribosome. Structural biology is really such an elegant and interesting and difficult area. I have great admiration for the people who solve these structures, and I hope next year actually to meet one of them in Israel. So yes, let's schedule it, and I will continue my ribosomal due diligence. Make sure I've turned every corner of the literature. Hard, but not impossible.
Sure. And when is your book coming out? The book you were referring to, or the chapters you're writing for the book?
I'm hoping early in 2023. And I'm trying to write the book in such a way that it's not just another critique of common descent. I want it to be a real intellectual adventure, and to bring the reader along in such a way that they feel they can't put the book down. I'm a great admirer of the nonfiction writer Michael Lewis, who is able to take very technical topics like how the stock market works and make them really into mystery things where you feel like you just can't put the book down. So I have a ambitious goal set for myself.
Brilliant. Thank you so much, Paul. It was a pleasure having you. For everybody else watching, we are going to be back live again in a few weeks' time, inshallah. So until next time, assalamu